Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module Pressure Assisted and Liquid Phase Sintering from the paper Processing of Ceramics. So students, let us see what we are going to learn in this module. In this module, we will be learning basically two main types of sintering. First is pressure assisted sintering and the second one is liquid phase sintering. In the last two modules, we discussed the solid state sintering of ceramics. In most cases, this is carried out without an external pressure. However, in techniques called hot pressing and hot isostatic pressing, an external pressure is applied to further improve the sintered density or for some composite which cannot be sintered otherwise. So in hot pressing, a uniaxial pressure is applied, while in the hot isostatic pressing, the applied pressure is isostatic. During the solid state sintering, no significant amount of any liquid phase is present. However, in many cases, a liquid phase is present during sintering. So the presence of liquid phase in these cases gives a high sintered density at very low temperatures. In this module, the pressure assisted sintering and liquid phase sintering will be focused and discussed. Now first we are discussing the effect of pressure on driving force and vacancy gradients. We have already discussed in the introduction that in the previous modules we have discussed the driving force for sintering and we have seen that it varies with 2 gamma by r. But on the physical level, an additional vacancy gradient is set up due to the applied pressure between the grain boundary and the neck. So when we talk about this, the change in the Helmholtz free energy is given as dA, which is equal to minus S dt minus P dV. At a constant pressure, this becomes P is equal to delta A by delta V. So multiplying both sides by atomic volume omega, we get P omega is equal to delta A omega by delta V, and we get minus delta A by delta N, where N is the number of atoms in volume V. Thus, on application of pressure P, the free energy per atoms on the chemical potential mu is decreased by an amount equal to P omega from the chemical potential over a stress-free surface mu naught, that is mu is equal to mu naught plus delta A by delta N, which is equal to mu naught minus P omega or mu naught minus sigma omega. So we get delta mu is equal to minus sigma omega. Here the term P has been replaced by sigma to take into account the fact that the external stress can be both tensile and compressive. Now, the concentration of vacancies under a flat and stress-free surface is given by C naught is equal to K exponential minus Q by KT, where Q is the enthalpy of formation of vacancies and K includes the entropy and pre-exponential terms. When an external stress is applied, the chemical potential of an atom is increased by delta mu. So the vacancy concentration now becomes C is equal to K exponential minus Q plus delta mu by KT. which is equal to 1 plus sigma omega by kT times C naught. So in the present case, sigma is the effective stress at the boundary. If a pressure is applied, then sigma is negative and the concentration of vacancies at the boundary is lower than at the surface, so that there is a net flux of vacancies from the pore to the grain boundary, which aids in pore removal. So now we will discuss about hot pressing. In hot pressing, a uniaxial pressure is applied to the parts during sintering. The pressures used are 10 to 70 megapascal, but it can exceed 200 megapascal in rare cases. The piston and the mold have to be made of a material capable of withstanding stresses at high temperatures. In this case, graphite is the most used material for this purpose because of its high strength, which increases with temperature, and graphite can be easily machinable and lack of reaction with the ceramic powders is there. However, graphite can be used only in an inert or reducing atmosphere. The use of pressure makes it possible to achieve nearly full density with a fine grain size and at a lower temperatures. It is possible to sinter some composites which cannot be sintered by pressureless sintering, such as Al2, O3, silicon carbide, etc. composites, but the process is expensive and is used only when the additional cost is justified. Hot isostatic pressing. In hot isostatic pressing, instead of a uniaxial pressure, a hydrostatic pressure is applied through a pressurized gas such as argon. Parts of complex shape can be manufactured, and the green compact has to be encapsulated in a foil of soft stainless steel for low temperatures and a refractory metal such as tantalum, molybdenum for higher temperatures. Alternatively, pre-sintering of the part can be carried out to make it strong enough for handling and coating it with glass powder, which at high temperatures forms an envelope around the part, making etching is hot isostatic pressing possible. Often a part is first sintered in a pressure-less manner and then subjected to hot isostatic pressing to remove the remaining porosity and to achieve dimensions with a very good tolerance. Hot isostatic pressing equipment is very expensive, so the process is to be used only when the very high cost can be justified. Now, in liquid phase sintering, if a liquid is present during some part of the sintering cycles, then the process is called liquid phase sintering. The liquid can be transient or persistent. A majority of ceramic products are manufactured using liquid phase sintering, and most of the traditional ceramics we have discussed earlier also, such as sanitary wares, tiles, etc., have siliceous liquid phase present during sintering. So some of the examples of non-traditional ceramics are ferrite magnets, covalent ceramics such as silicon nitride, ferroelectric capacitors, tungsten carbide with cobalt for cutting tools, etc. Now let's discuss the various stages of liquid phase sintering. So in general there are three stages. First is particle rearrangement, second is solution reprecipitation, and third is solid state controlled sintering. So we will be discussing all these stages one by one in the following slides. So the first is particle rearrangement. In particle rearrangement, capillary forces develop because of the presence of the liquid in the powder compact. These forces pull together the particle and produces a large amount of densification simply by a rearrangement of particles. To understand how these forces develop, let us consider a model case of a liquid drop trapped between the two plates, which is shown in this figure. The two cases are considered in figure A and B. In one case, that is A, the liquid has large contact angle with the solid plate, while in the other, the contact angle is small. The contact angle is always measured inside the liquid, and note that smaller the contact angle, better is the wetting of the solid by the liquid. The liquid vapor surface energy is denoted by gamma LV. The radius of the circle of contact of the liquid with the plates is x, and rho is the radius of curvature of the liquid drop. Now considering the figure A, the component of force due to gamma LV, that is the liquid vapor surface energy, is given as FL is equal to gamma LV cos of theta minus 90, which is equal to gamma sine theta. This component acts downwards and pulls the plate together. Smaller the value of contact angle, larger is the pull. The excess pressure inside the liquid due to curvature is given as 2 gamma divided by rho. The equation 2 acts as the periphery of the liquid plate contact circle, while the third equation acts as the area of the circle. The net force due to the 2 is given as minus gamma sine theta into 2 pi x plus 2 gamma divided by rho into pi x square. The first component, which attracts the plates together, is usually smaller than the second component, which repels the plate, and so the net effect is that the plates are repelled. When the contact angle is small, as shown in figure B, the net force is given as minus 2 pi x into gamma sine theta minus 2 gamma by rho pi x square. In this case also, both the components are attractive, and so the plates are pulled together. Therefore, in the case where liquid wets the solid particles well, an attractive force acts between the particles, which tend to pull the particles together. Therefore, for effective liquid phase sintering, the liquid formed during sintering should be a wetting liquid. During the firing cycle, when the liquid forms, it pulls together the particles in contact with it. The solid particles pack closely together due to this pull, and there is a large densification which occurs due to this particle rearrangement. About 35% by volume of liquid will fill the interstices between the solid particles completely and gives nearly 100% density, that is, liquid is fully wetted. However, the amount of liquid is usually much smaller except in the cases where it is deliberately kept high. It can be shown that the net pressure on the whole compact due to the surface tension force is given as delta P, which is equal to 2 times root of 2 pi gamma by r cos theta, which is equal to 9 megapascal typically, where r is the particle size, and the above relation show that the effective particle rearrangement is favored by a small particle size, small contact angle, and a high value of liquid vapor surface energy. So in continuation with the previous slide, the amount of the liquid that can be present in a system consisting of ceramic particles surrounded by liquid depends on the dihedral angle between solid and liquid. This figure shows the result of the calculation of the energy of system as a function of volume fraction of the liquid for different dihedral angles. For each dihedral angle, there is a minimum in energy at a certain value of the amount of the liquid phase. These values of the liquid phase versus dihedral angle at minimum of energy is also plotted in figure B. The figure shows that the amount of liquid phase that can be tolerated by the system increases as the dihedral angle decreases. It reaches about 30% when the dihedral angle is 0, that is, the liquid wets the solid particles perfectly. It approaches 0 when the dihedral angle is about 40 degrees. So, if a larger than maximum possible liquid phase is forced up to the system, then there is swelling and liquid break out. Now we are discussing the second stage of liquid phase sintering, that is solution reprecipitation. The particle rearrangement gives a very significant increase in the density. However, as the particles may have sharp edges and corners, they do not pack very efficiently. The solution precipitation mechanism removes the sharp corners and allows the particle to come closer together to yield further densification, as shown in figure. The solid phase always has a finite solubility in the liquid phase, and the sharp corners and edges of the particle dissolve in the liquid to a large extent due to chemical potential differences. The solid is transported through the liquid from the sharp corners to less sharp corners near the same and other particles. The concentration of solid species near these less sharp corners increases beyond the equilibrium value and the increased deposits on the solid particles. This causes rounding off of the sharp particles, which can then come closer together, leading to a further increase in density. So the time required for a given amount of sintering to occur due to solution reprecipitation is given by T is equal to beta r to the power 4 k T divided by d gamma delta omega. Here r is the particle radius, dl is the diffusion coefficient of solid spheres in the liquid, delta L is the thickness of the liquid film, omega is the atomic volume. Note that the time increases as fourth power of the particle size, and a small particle size is therefore desirable to achieve good densification. As the diffusion coefficient depends exponentially on temperature, the liquid phase sintering is much more sensitive to temperature than the solid state sintering. The liquid phase sintering can be carried out at a much lower temperature than solid state sintering. Now the last stage is solid state controlled sintering. At the end of the second stage, most of the densification has taken place. After the first two stages, a solid skeleton exists with liquid in between, and further sintering can now occur by solid state diffusion, while some solution precipitation or solution reprecipitation process continues. Grain growth occurs in this stage, and this stage does not lead to much increase in the density. On the other hand, the properties are generally degraded in this stage. So this stage should be kept as short as possible. The many advantages of liquid phase sintering have already been discussed, but the liquid phase sintering may not be suitable for those applications where the components need strength at higher temperatures. Also, the presence of second phase may degrade chemical and other properties even at lower temperature. It should be, however, pointed out that trace amount of a liquid phase is invariably present even in the high purity ceramic due to siliceous and other properties. For example, in silicon nitride, a few angstrom thick layer of yttria silica film is found to be always present at the grain boundaries. So students, let us summarize what we have learned in this module. So first it was pressure assisted sintering. So in this, a pressure is applied during sintering. That's why it is called pressure assisted sintering. And the external pressure directly adds to the driving force, which varies as 2G by R. The concentration of vacancies near grain boundaries is increased, and there is increased diffusion of vacancies from grain boundaries to pore, leading to increased densification. So the pressure may be uniaxial or isostatic, and for these cases we have read that it is hot pressing or hot isostatic pressing. So these pressing techniques are quite expensive and are used to sinter difficult ceramic products. They can produce some parts with nearly 100% density. So liquid phase sintering is the second sintering which we have read, and in this some liquid is present during some part of sintering cycles, and the initial densification occurs due to particle rearrangement due to capillary forces. So further densification occurs by solution reprecipitation, in which the sharp corners and edges of the solid particles are dissolved by the liquid and transported through the liquid and deposited elsewhere, leading to a rounding off the grains. So this rounding off allows the grains to pack better and so cause an increase in the density. And towards the end of the cycle, the solid state controlled sintering starts, which is undesirable and should not be prolonged, which we have discussed clearly in the module. So these are some advantages of liquid phase sintering. That is, it produces faster densification due to faster atomic diffusion and due to particle rearrangement. The grain size can be easily controlled. Next is, systems which are difficult or impossible to sinter by solid state sintering can be sintered using liquid phase sintering. Moreover, that trace amount of liquid phase is invariably present even in the high purity ceramic due to siliceous and other impurities. So for example, in silicon nitride, a few angstrom thick layer yttrica silica film is found to be always present at the grain boundaries. So the disadvantages of liquid phase sintering are, liquid phase sintering may not be suitable for those applications where the components need strength at very high temperatures, as the glass phase at the grain boundaries soften at higher temperatures. Also, the presence of a second phase may degrade mechanical and other properties even at lower temperatures. Thank you.